Welcome yet again. Where are we coming from? This is today's topic, reacting volume of gases. But even how did we get here? We have come, I think, quite a bit way. Started with the way back, I think, lesson 1 to 4 to lesson 5 there. Started with what? Moles of simple elements, which I guess, mention or we mentioned that if I have an element, consider what aluminium, it has a relative atomic mass of 27, or if I convert this one to gram to get 27 grams, 1 mole of aluminium will always be equals to 27 grams. Okay? Or if I have 27 grams of aluminium, I know this equivalent to of compound out its relative molecular formula. Okay? From the relative molecular formula, we get the formula mass, and that one becomes its molar mass. Okay? That's number two. Okay? From there, I think we also discovered somewhere about reacting volumes of gases, right? Not yet the volumes of gases, but the volumes of gases in relation to the what there is that at room temperature and pressure, one the gas which you take, temperature is 25 degrees, is 1 atmosphere. Okay, the volume occupied by 1 mole of any gas is 24 dm cubed, which is equal to 24,000 centimeter cubed. Okay, we did some calculation related to that one. And I think after that, we come across this the reaction or the molar reactions or molar ratios in chemical reactions. Where we say, if you consider a reaction, let's say reacting magnesium in oxygen, it would be magnesium oxide. This is a solid, this is a gas, and this is a solid. If I come here and make sure that this equation is balanced, I balance it. So it's balanced so that on the left hand side we have the reactants, and on the right hand side we have the products. And what this one came to tell us is that 2 moles of magnesium reacts with the 1 mole of oxygen gas to give 2 mole of magnesium oxide solid, right? And if we is referred to sometimes back or to the other lessons so that we move forward. These things they are interrelated. So as we say here, volumes of gases, then let's get right into it. Okay. Just the way we talked about reacting the solids in the previous topic. Let's consider a case whereby I burn nitrogen gas or nitrogen gas reacts with the oxygen gas, for example, to give us the nitrogen dioxide gas in such a way. Okay, all of them are gases. This one. Okay. Let's try to balance this equation. Always, in this case, everything is gas, gas, and gas. Okay. Um, we balance two nitrogens there. Then we have like 1 nitrogen. We can put a 2 there. So we have 2 nitrogens on both sides. Then 2 oxygen on the left hand side, 4 oxygen on the right hand dioxide, so we can add it there. When I say in this chemical reaction, we make sure that it's well balanced because if it is not correctly balanced, you have a problem because we are about to come up with some implication. In this case, we are saying that in this particular reaction, 1 mole of nitrogen gas reacts with the 2 moles of oxygen gas to output or to give out as product 2 moles of nitrogen gas. I'm taking the coefficients of our particular products there or the balancing quantity. But remember the other time we said that one volume or 1 mole of any gas, 1 mole of oxygen, 1 mole, 1 mole of nitrogen gas, 1 mole of carbon dioxide gas. All of them, if we were to look at how the amount of volume they occupy 24 billion cubed or 1,000 centimeter cubed, 24,000 centimeter cubed. Okay, so when I'm dealing with the gases in all my reactants are gases and the products are gases, I can safely say that I am reacting 1 volume of nitrogen gas with the 2 volumes of oxygen gas to give me 2 volumes of nitrogen gas. In this case, I am essentially saying this that if let's say I reacted 20 centimeter cubed of nitrogen, I need to react it with 40 centimeter cubed of oxygen gas, and it will give me 40 centimeter cubed of nitrogen dioxide. Okay, this is a little bit different from when we had solids. When we had solids, this and this would not be implied. Okay, or wasn't implied. So in this case, this one rhymes. And why is it rhyming or is it true? It's because we have already said that if I am considering 1 mole of any gas, it must occupy the same space. So if I said the other time, or if we said that if I have a tank of just 10 centimeter, for example, by 10 centimeter, by 10 centimeters, a small tank, and it is full of oxygen, and I have another tank, again 10 centimeter, by 10 centimeter, by 10 centimeter, and it is full of carbon dioxide, saying that the number of moles inside here is equal to the number of moles inside here because the volume of this container is the same as the volume of this container, and we know that at room temperature and pressure, gases, equal volumes of gases, they contain the same number of moles of that particular gas we are talking about, right? So or consider, so to solidify the concept, consider a case whereby that in the previous equation, this same equation, let me do some wrapping here. So, bring up. Ah, this equation is saying that we have said one volume, and consider it 1 mole of nitrogen dioxide is reacting with 1 mole of volume of with 2 moles of oxygen to give me 2 moles of nitrogen dioxide. So the question would be something like this. Um, 8 grams of oxygen was used. If let's say we use 8 grams of oxygen gas in this reaction, how many moles of nitrogen dioxide was produced? What is the volume of nitrogen dioxide if it was produced? What's the mass of nitrogen dioxide if it was produced? What is the mass of nitrogen used? So the questions here. If this is the oxygen, the number of grams of oxygen which we reacted, let's look out for uh, one moles of nitrogen dioxide produced, two mass of nitrogen dioxide produced, mass of nitrogen gas which was used in the chemical reaction. So let's start. So what do I do? I'll start by to this one a bit to understand I said volume, say nitrogen dioxide into produced. This is produced. So what do I do? My first step is to go ahead and, as I say, I can either do of volumes or in terms of moles. Because we are doing with reacting volumes of gases, let's just go ahead and use the volumes of gases. But I'm saying whether we use the volume of gases or volume or moles of gases, it's all the same. So, but but since we are coming from where we have been talking so much about moles, let's do the volume of gases. So I know this that one mole of oxygen gas is at room temperature and pressure. It's always 24 dm cubed. Okay, and if it is 24 dm cubed, it must be it is 24 dm cubed because it's one mole and must weigh what? Oxygen. It's yes, two oxygen molecules, so its relative molecular mass is 16 divided by 2, which gives me that 2 grams. Okay, so 24 dm cubed of oxygen is at 2 grams. So if I have 8 grams of oxygen, what's the volume that it occupies? Okay, the implication we remember that one is not going away. Then my answer becomes x multiplied by that 2 is equals to 24 multiplied by 8. So that's 2 divided by that 2. This is making x the subject of the formula. That one was by 8 1 by 8. Is 4 by 4 1 by 4 is 6. So it means that I reacted 6 dm cubed of oxygen or 8 grams. 8 grams is a volume is a volume of 6 dm cubed of oxygen in room temperature pressure. So if I come to my equation here, let me pick a different pen. Coming to our equation here, it means that I already said that one volume of nitrogen gas reacts with two volumes of oxygen gas to give me two volumes of nitrogen dioxide. So in this case, I have 6 dm cubed of nitrogen gas, of oxygen gas. So what is the volume of nitrogen do I react? Look, what has been get from 3 to 2 or the ratio of from oxygen to nitrogen is 2 is to 1. So this I need to get, how do I get 1 from these two? I divided this by 2 to get 1. So I need to divide this one by 2 and then the answer would be I will get 3 more, 3 there. 3 volumes or 3 dm cubed. Uh, 2 volumes of oxygen gas produces 2 volumes of nitrogen gas. So what will I get? I'll get 6 dm cubed of nitrogen dioxide gas. Right? So what is the question asking? The moles of nitrogen gas produced. So if I know that my question over there, the first question over there. The most of nitrogen produced, with that, but you will be able to follow. So you are writing as we say. I know that 1 mole of nitrogen dioxide must be equal to 24 dm cubed. That one we know. In this case, I have 6 dm cubed of nitrogen. How many moles is it equal to? Always write terms together. So cross multiply. We are going to get x multiplied by 24 is equals to 1 multiplied by 6. By 24 divided by 24. The subject of the formula by 6, 1 by 6, this is 4. This is 0.25. That's a quarter of a mole. That is the moles of nitrogen dioxide that will be produced. Okay. The second question: mass of nitrogen dioxide produced. Right. You can use the calculated volume. But as I said before, if you have a problem with your calculation and you get the wrong answer there, if you use the calculated volume, you are likely to propagate the error to the second answer. So instead of using the calculated volume, we are going to use same 6 dm cubed, the 6 dm cubed, which we know to be the volume of our starting point. So we want to know the mass of nitrogen dioxide produced. So we start by finding the formula mass for nitrogen dioxide. Where is this pen? Where is this pen? Nitrogen dioxide is there. So nitrogen is equal to 40 plus or 2 oxygens is 2. This one gives us 46. Okay, that's the formula mass for this one. For 1 nitrogen plus 2 oxygens. So it gives us 46. Okay, so I know what this is the 46, which is the formula mass. Formula mass is equivalent to the mass of 1 mole of nitrogen dioxide, which I also know it is equal to 24 dm cubed. So what am I going to say? I'm going to say that I know 24 dm cubed of nitrogen dioxide must have a mass of 46 grams. What about 6 dm cubed, which is what we have of is equals to what mass x. Okay, we are going to get our like this 24x. 24x is equals to 6 multiplied by 6 divided by 24 both sides. 24 divided by 24. So the x of course is subdivided by 4. I mean by 6 1. 6 is 4. By 2 is 2. By 2 is 23. And by 2 is 1. By 2 it should be 11.5 grams. And that is the mass of the nitrogen dioxide that is produced in that particular reaction, right? That's the second step. Then the number, or the other one is the mass of nitrogen dioxide that is produced. So we need to clean up the so we are saying that we want to know considering the mass of nitrogen which was produced. Okay, now we say we produced air cube of nitrogen gas. Nitrogen gas is our nitrogen gas. Its formula mass is 14 multiplied by 2, which is 28. 14 is because the RAN, the relative atomic mass of nitrogen, is there is 14. But nitrogen gas contains two atoms of nitrogen, so its mass is 28. So this is a because we are dealing with the moles, we are putting them in grams. So I'm saying that 24 m cubed of nitrogen must always weigh 28 grams. But if I have a 3 dm cubed, those ones there, which took part in our chemical reaction, those ones will be equivalent to what? An x. Doing our cross multiplication, we are getting 24 multiplied by x is equal to 3 multiplied by 28. And then you divide by 4 divided by 4, making x the subject of the formula. 3, 1 by 3 is an 8. By 4 is 2, by 4 is 7, and this one gives me 3.5 grams. Remember always to put the correct mass or the correct unit. In this case, grams where it is grams, put grams where it is moles, it's moles, right? Now, volume of nitrogen dioxide produced. This one I think we already found it. It was right. Okay. Consider this other one whereby we have something like magnesium reacting with dilute hydrochloric acid to give magnesium chloride plus a hydrogen gas. Okay, it's also involves some gases somewhere. Magnesium is reacting with HCl to give us magnesium chloride and hydrogen gas. Right? This is a solid. This is an aqueous solution. Aqueous solution. Balance the equation: one magnesium, one H or hydrogen, two hydrogen. So we need to convert this to chlorides. So it is balanced like that. Okay. Yeah. So then want to consider suppose that use is the grams of magnesium, how much hydrogen is produced. Then it is a good number. So that we don't confuse ourselves. It isn't a big deal. 50 grams of magnesium, 50 grams of magnesium is used. How much is produced at room temperature and pressure, right? So 50 gram, 50 gram, first of all, we take the ratios. We say that just like the other time, this is 1 mole of magnesium reacts with the 2 moles of HCl solution to give 1 mole of magnesium chloride and 1 mole of hydrogen gas, right? So I need to calculate how many moles are in 50 grams of magnesium, and because magnesium it should be 24, yeah, it's right here, here is 24. So find the moles of magnesium. Remember, we said that 1 mole equals to 24 grams. What about 50 grams? I mean, moles are there. X. Do some cross multiplication there, and we're going to get 24x is equals to 50 divided by 24 divided by 24. This one will give us our x will be, let's see, by 2 is 4, by 2 is 25. Use our calculator somewhere. So in our solution, in our equation, when we are saying that 2.1 moles of magnesium was used, and we can use a different pen here or with clarification purposes. 2.1 moles of magnesium was used, 2.1 mole was used of magnesium. So how many moles of HCl were used? Is we multiply this quantity by 2, so it becomes 4.2 moles of HCl was used to produce 1 mole again. It goes with again 2.1 mole, and of course 2.1 mole of hydrogen gas was produced. So if I know that the moles of hydrogen which was produced, now I can easily find the volume of hydrogen, because I know 1 mole of hydrogen at room temperature and pressure is 24 bm cubed. 2.1 mole of hydrogen is equals to what? Okay, and this is multiplication here. I'll get x is equals to 2.1 multiplied by 24. So it means that it is 2.405. One decimal point there, and this one gives us is 3.4 volume of hydrogen that was produced. Okay, so so far so good, and related to this is the concept we have been talking about enough quantities, whereby when I'm reacting, let's say with HCl, there is enough hydrochloric acid to react all the magnesium. Okay, when I'm reacting nitrogen with oxygen, there is enough oxygen to react all the say nitrogen. But suppose we have a case whereby one of the component in the reaction is not sufficient. In such a case, we have what is called a limiting reaction, or where one of the reactants is called a limiting reactant. A limiting reactant is the reactant which gets used up 100% before the corresponding reactant could be used up, or could be used at 100%. Let's start with a simple one, like let's burn, say we are burning magnesium again in oxygen gas. We know this one always produces magnesium oxide, right? And is this efficient balance? No, it is not. So we have equilibrium because of the oxygen, and then we push in here. So under normal circumstances, it means that we are supposed to react 2 moles of magnesium with 1 mole of oxygen gas, so that we always get 2 mole of magnesium oxide. If we are to talk in terms of real masses, suppose I have like 24 grams of magnesium, or 24 grams of magnesium, right? Let me make also so that it makes absolute sense. I need this one to be 48 grams, for example. 48 grams of magnesium is equal to 2 moles. Okay, so if I have 48 grams of magnesium, which is equal to 2 moles magnesium, it should react with 1 mole of 1 mole of oxygen, which I know it is that 2 grams or 24 dm cubed, all right? And to give me 2 moles of magnesium oxide, and 2 moles of magnesium should approximately be, let's say, do this calculation. 2 magnesium is 48, 2 oxygens is no, yes, 2 magnesium is 40, 2 oxygens is 32, is 0, 80. So this one will give me 80 grams of magnesium oxide. This is a complete reaction whereby we had enough magnesium and enough oxygen, so that the equation went to completion, right? Now, saying is that many of the instances will be such that one of the component will be a little bit more than what is required by the other one. So suppose consider this reaction. Suppose I have like 6 grams of magnesium. I'm sorry, suppose I have like 6 grams of magnesium. 6 grams of magnesium. Right? Then I have all this a gas jar, which is 100 centimeter cubed, which is full of oxygen. I can make it 1,000 centimeter cubed, which is like 1 dm cubed, 1 dm cubed of oxygen gas. All right, it's there. It's closed to begin with. So we have our O2 inside here. Then we take our magnesium. This is our 6 grams of magnesium, which is a silvery shiny strip of metal. And this particular apparatus has a cover which, when I lower it over this gas gap, it will be able to close here so that we don't get any more oxygen coming in. I hope that makes sense. So this is a cover. This is a glass cover. So if I'm looking at from the top, this part here, this part A is a round thing which is enough to cover the mouth of this whatever. So the moment I take out this cover, I push this, I'll first of all start burning it slightly, and then immediately I drop it into this oxygen like that. Okay, it will burn a little bit, it will burn, and some white powder will be formed. Under normal circumstance, when you have excess oxygen, this thing is supposed to burn all of it so that you have only white powder remaining. But what will happen is that if I have 6 grams here, 6 grams of rich magnesium, it will start burning, and then it will use up all the oxygen which is in this gas jar. And after that, the reaction stops. All right. So if the equation stops, now we needed to find out what was limiting in this reaction, what was not enough, right? And how do we do that? Let's start because let's start with our oxygen. We are given 1,000 centimeter cube of oxygen. 1,000 centimeter cube of oxygen. We want to find out how many moles of oxygen are there. But we know that 24,000 centimeter cube of oxygen is equals to what? Is equals to 1 mole. So I want to know in 1,000 centimeter cube how many moles of oxygen are there. All right? I hope I'm clear there. I'm saying we only had a gas jar which had 1,000 centimeter cube of oxygen. I know that 1 mole of oxygen is always 24,000 centimeter cube at room temperature and pressure. So cross multiplying here, finding my mole, I'll find x multiplied by 24,000 is equals to 1,000 divided by 24,000 divided by 24,000. So I'll get my x, or the moles of oxygen, is 1 over 24. If we do our calculator here, we'll get the moles of oxygen is 1 divided by 24. Okay, which gives us something like 0.042, 0.042, and usually two decimal places. So 0.042, 0.042 moles of oxygen. So now you see, this is the number of moles of oxygen which we have. Uh, Let me look. If I have 6 grams of magnesium, how many moles of magnesium are those? I am going to divide. I can do the same. 1 mole of magnesium is equals to 24 grams. What about 6 grams? How many moles are there? And once you do your cross multiplication and divide, you find x is equals to 6 over 24, which is 0.25. So this 0.25 moles is way bigger than this one, so that the limit, my limiting quantity or my limiting reactant is oxygen. So that's what I'm going to start with, and that is very important, that I have 0.042 moles of oxygen. So it means how many 0.02, 0.042 moles of oxygen, how many moles of magnesium can it react? It can only react 0.084 moles of magnesium. How many moles of magnesium oxide is it going to produce? It can only produce 0.084 moles of magnesium oxide. So I multiplied this one by 2 because here 1 has been multiplied by 2 to get 2. So I multiplied this by 2 to get this guy. This one has been multiplied by 2 to get this one. So this one multiplied by 2 to get that one is times 2. Similarly, I multiply this by 2 to get that one. So in that mass of 6 grams of magnesium oxide I was given, the only mass of magnesium I'm going to use, or which will react, will be only 0.04 moles. So how many grams of magnesium am I going to use? I know that 1 mole of magnesium is equals to 24 grams, right? So if I have 0.084 moles of magnesium, it's equal to how many grams? I'll do some cross multiplication, and I'll get my x is equals to 24 multiplied by 0.084, and picking our calculator here. Calculator down here, and trying our multiplication, we do 24 multiplied by 0.84 equals 2.01. 2.01. That's correct. That's correct. So this one is coming to 2.0. Is it 2.01 or 2.02? Two decimal places. 0.02, 2.02 grams. So out of the 6 grams, we'll use only 2.02 grams of magnesium strip, and therefore at the end of the reaction we have some remaining magnesium which hasn't reacted, and that amount of magnesium is equivalent to 6 minus 2.02, and this one I think it will be 3.98 grams. Okay, this minus this should be this one. This one will find it equals to 6. So this magnesium will remain unreacted. Okay, so in this container at the end of it, you have some 3.9 grams, almost 4 grams of magnesium remaining, and some mass of magnesium oxide. So how much magnesium oxide will be there? Okay, how much magnesium oxide will be there in terms of mass? Clear that put it clearly, all of it at the same time. And so, how many magnesium oxide, quantity of magnesium oxide there that will be produced? Here we are. We know that we produced 0. We know that we produced 0.084 moles of magnesium oxide. Okay, so if we produce 0.084 magnesium oxide, we know magnesium oxide, that is the formula. So it is 24 plus 16, which is equals to 40, right? The formula mass. So I'll say 1 mole of magnesium is equals to 40 grams. So if I'm dealing with 0.084 mole, what is the mass of that? And I do cross multiplication, I'll get that my x is equals to 40 multiplied by 0.084. So this one should be easy multiplied by 100. The decimals and zeros and multiply plus of 4. Uh, 84 by 4 is 16, 16 carry 6 carry 1. The 8 by 4 is that 2 plus 1, that 3. This 0 is that one there. I have added it there, the 1, 2, 3 decimal places. 1, 2, 3 decimal places there. So we are going to get 3.336 grams of magnesium oxide. So in this container, there will be 3.9 grams of magnesium, and 3.36 grams of magnesium oxide, right? Okay, okay, okay. So looking at a different one. So from here, what we notice is that the product which or the molecular product that is the input, the reactant which did not finish or which is excess, is essentially called excess reactant. It's never used up, right? The one which is used up in this case, it's our oxygen, is called the limiting reactant. Okay, and the amount of product, the amount of magnesium oxide we produce, the amount of product which is produced is always determined by the quantity of the limiting reactant, not the excess reactant, but the limiting reactant. Let's consider this other one, whereby we are reacting calcium with the excess hydroxide, the excess hydrochloric acid. We have 4 grams of 4 grams of calcium, and we want to react it with the HCl. So the equation is that HCl plus calcium. Of course, this one will give us calcium chloride plus some hydrogen gas. Okay, try to balance this equation. Try to balance it. Uh, calcium is okay. I think I've started with calcium, but it's still okay. Doesn't matter. Then chloride ions, they are not balanced, so we can put a 2 there. And now we have 2 hydrogens, 2 hydrogen, 2 chlorine, 2 chlorines, and 1 calcium, and 1 calcium. It's balanced. So the equation is like 2 moles of HCl reacts with 1 mole of calcium to give 1 mole of calcium chloride and 1 mole of hydrogen gas. So those ones, they are here. We just don't put them because when we say one, it's essential there, right? And then of course state symbols. This one is AQ. This one is a solid. This one is an aqueous solution. This one is a gas, right? Now, in this case, we are told that we already know that it's calcium being reacted with excess HCl. And we want to look at how much hydrogen, for example, is produced, how much calcium chloride in reality that is produced. So let's find out how many moles of calcium that we have, that we do have here in that equation. And we already know calcium should be number 40, or should have the is there. It has an RAM of 40, so 1 mole of calcium is equal to 40 grams. Let's use this down here, okay. So 1 mole of calcium is equals to 40 grams. So if I have 4 grams, note I always putting the right terms together. So I am getting that 40x is equals to 4. Okay, and then x is equals to 4 over 40, dividing by 40 both sides trying to make X the subject of the formula by 4,1 by 410, and this one gives me 0.1 mole of calcium. So 4 grams is equivalent to 0.1 mole of calcium. So I come to my equation in here, okay, and I'll say that instead of 1 complete mole, I have 0.1 mole of calcium. So it implies how many moles of the excess hydrochloric acid am I going to use? I'll be using, this one has been multiplied by 2 to get 2, so I'll multiply this by 2 to get 0.2 mole. Okay, so the 1 mole of calcium produces 1 mole of calcium chloride, so 0.1 mole will produce 0.1 mole. Okay, 1 mole of calcium produces 1 mole of hydrogen gas, so 1 mole of 0.1 mole of calcium will produce 0.1 mole of hydrogen gas. Okay, so what's the volume of my hydrogen gas that do I produce? I know at room temperature and pressure, 1 mole of hydrogen must be equal to 24 dm cubed. So what about the 0.1 mole? It will be equivalent to what? And then doing my cross multiplication, I'll get that my x is really 24 times 0.1 dm cubed. And this one will be equivalent to 2.4 dm cubed, right? So always, I think the other question was asking about maybe the mass of calcium chloride that we are going to produce in there, although it is already dissolved, but we can find it. It's will be given by what? I need to find the formula mass for calcium chloride, and the formula mass will be one calcium plus 2 chlorides. 1 calcium is 40 plus 2 chlorides. 1 chloride is at 5.5. This is 40 plus this is 1, and this is 111 grams. Okay, so I will say the next step of the equation is that if 1 mole of calcium is equals to 111 grams, what about 0.1 mole? Because that's what I have right there. 0.1 mole is equivalent to what? Is equivalent to x. I cross multiply, and this one will end up giving my x is equals to 0.1 multiplied by 111, which will give me 11.1 gram. That is the mass of calcium chloride which will produce. Of course, it doesn't come out as a solid. It comes out, it's already dissolved in water. That's why the state symbol is there, the aqueous solution. So the most important thing in this kind of equation is to realize what is the limiting what do you call it, limiting equation or limiting substance, because the limiting substance is the one which is going to control what it is that you produce and the masses that will be produced always. That is usually the case, that the limiting solution and the limiting component. The component which is not enough is what will always determine how the whole reaction will look like. Okay, and this one, it can also be true even when you react volumes of gases, the one we referred to before. You may have been given some volumes which are not enough. For example, consider a case whereby we are burning hydrogen in oxygen to form some steam or some water in gas form. Okay? Yeah, consider this one. We try to explore the hydrogen gas in oxygen to give this one always gives you the water, and all of them they makes it gas. This gas water is because it will come on as steam, of course, it will condense in some moment to become liquid. Okay, so that's the equation of the reaction. Now, hydrogen gas reacting with oxygen gas to give us water. It's not balanced. We need to balance it. I said always it's hard to balance with negative odd number of some elements. This is an odd number. I make it 2. Now it should be easier to balance it, and therefore I need to put a 2 here. So 4 hydrogens, 4 hydrogen, 2 oxygens, 2 oxygen, and the equation is balanced. So this one tells me that when forming the water molecule, 2 volumes of hydrogen gas must react with 1 volume of oxygen gas to give 2 volumes what of water in steam form. So if I have a case whereby, let's say I have a limited quantity of one of the substance, um, the the other one will be left not used. So for example, we see 2 volumes of hydrogen are reacting with 1 volume of of, uh, of oxygen. Suppose we are given something like 48 dm cubed of hydrogen gas was reacted with, for example, 6 dm cubed of oxygen gas. Okay, uh, find the amount of water produced produced plus excess volumes, or if any. Okay, so suppose we are given 48 dm cubed of hydrogen gas, and we were given only it was exploded in 6 dm cubed of oxygen, for example. Find the amount of water that was produced in this reaction and excess volumes, if any. Okay, so let me start first of all by looking at the 22 at hydrogen. Consider, considering hydrogen, considering hydrogen, I'm going to see that if I have 48 dm cubed, 48 dm cubed, and then 48 dm cubed, this must be equal to x, but 24 dm cubed must be equal to 1 mole or 1 mole, which is equivalent to 1 volume. So if I do cross multiply, I'll get my 24x is equals to 48. So my x is equals to 48 over 24, which is equals to 2 mole. Okay, so this one tells me that if I have I, I have 2 moles of hydrogen gas. If I have 2 moles of hydrogen gas, it means I must have 1 mole of oxygen gas. But is the 6 dm cubed equivalent to 1 mole of oxygen gas? It's not. It's equivalent to how many mole of oxygen, because that now becomes the limiting factor. So I'll say 1 mole of oxygen is equal to 24 dm cubed. What about 6 dm cubed is equivalent to what by x? Cross multiply like that. I get 24x is equals to 6 divided by 24 divided by 24. This one will give me by by 6 1 by 6 4. This is 0.2 of 5. It's a quarter more. So I have 0.25 more instead of what we needed. So in this case, I know that my limiting reactant is the oxygen gas, right? So we can come here either using our dm cubed, because we remember we said for volumes of gases, whether we go by volumes or by the number of moles, it's the same thing. It's the same thing. So to avoid using the calculated figure, I'll go with the volume. So I know I have 6 dm cubed of oxygen. How much hydrogen is it going to react with? It can only react with 12 dm cubed of hydrogen. Why? 1 volume reacts with 2 volumes. So 6 dm cubed reacts with the 12. 1 you multiply by 2 to get 2. 6 you multiply by 2 you get 12. And what's the volume of water which is produced? One volume produces two volumes, so 6 dm cubed will produce 12 dm cubed. All right. So what is the amount of water which was produced? 12. It's right there, 12 dm cubed. All right. What Find the excess volume. Excess volumes in this case is hydrogen. So initially, in that container or exploding container, we pushed in 48. We are looking at the volume of excess H2. Uh, pushed it 48 bm cubed, right? We used what? 12 bm hydrogen gas. So difference that 2 bm is 6 bm cubed of hydrogen was left or was excess. It did not react. Okay, so those are typical exam questions, and there isn't much which can be brought, just trying to confuse you here, and there, but otherwise it is it's, all the same. Which can I mean it's all the same once you understand the concept and you understand the background. You see we are bringing in the dm cubed, the centimeter cubed when in relation to volumes of gases at room temperature and pressure. We are bringing in the molar masses, the molar volumes. So it's like combining the previous knowledge, all of it, and getting you to understand it better. More importantly, especially when you are dealing this for this equation, is to make sure that you can write well balanced equation. Make sure you are good at balanced whatever equation you are given, so that because when the equation is well balanced, it makes your work very easy, or it reduces your chances of making an error when you are doing your calculations way forward. Okay, so as usual, remember it's not about learning and understanding it today. It's about seeing it, and the only way to see it is to for you to do lots and lots of exercises. So I think there's still one more subtopic remaining about the molar solution, which will be type 4 in the next few minutes. Do the work. It's important. It's only the work which is going to make you pass this particular thing. They are pretty easy once you know what you're doing, but you need to push in the